Hello everyone, welcome to our differential equation class. In this video we are going to talk about second order linear differential equations. This is a continuation of a previous video, so we are going to start reviewing what we saw in the previous video about these equations. Then we are going to show a theorem that says when these equations have solutions and when these solutions are unique. Then we are going to focus on properties of a particular type of these equations, which are the homogeneous linear differential equations. So homogeneous. To talk about these properties, we are going to introduce operator notation, and then the properties we are going to focus on are linearity and superposition. Then we are going to introduce what is fundamental solutions of these equations, and we are going to show a result about the general solutions of these equations. So this is the plan for today. Let's start our video today with a review of the previous video, where we introduced second order linear differential equations, which are equations that have this form. We have the second derivative of the unknown function, not just the first derivative and the function, but second derivatives. And then the equation is linear. As we can see here, the unknown function appears with power 1 or power 0. And the coefficients in the equation could be coefficients that depend on the variable t or not. And this is the non-homogeneous term. The main example of this type of equation is from physics, is the mass spring system. That is a system where we have a spring. We chose to hang the spring from the ceiling, and the spring oscillates in a medium that could be air or could be water or anything else. We have a mass here and the object hanging from the spring. And to describe this system, to describe the equations of this system, we introduce a coordinate system, and we chose, well, the movement is on the vertical direction, so the coordinate system is only on the vertical direction. We chose positive downwards, it's just a choice. So equilibrium, when the spring is at equilibrium, we said this is going to be the variable y equals 0. When it's elongated from that position, it's going to be positive, and when it's contracted from that position, it's going to be negative. And with that system, with coordinate system, one can check that the differential equation that satisfies this system is this equation here, where we have mass times acceleration of the object, and then equal, if we put here equal, some forces, which is the force done by the spring and the force done by the friction in the medium. When we put all the terms on one side, we have an equation of this form, where in this particular system the coefficients are functions that they are constant in time, and these coefficients have physical meaning. The coefficient k is the spring constant, the coefficient d is the damping constant, and here we have the coefficient m that we don't have here, but of course we can always divide by that coefficient, and then we have the equation in this form. So writing the equation in this form or dividing by m is not important. M is the mass of the object hanging from the spring. So these are the main system we introduced in the previous video, and we also introduced some notation. For example, we said that we are going to denote the velocity of the object, which is y prime, as v, and the acceleration of the object, which is the second derivative of y with respect to time. We are going to denote it sometimes as a, acceleration. And then we consider the case of no friction, and when there is no friction, for example, here we are oscillating in air, so then d could be positive or 0, so it's a good idea to clarify that. And in that case, when it's 0, the equation is simply lacking one term. The term with the derivative is the mass acceleration equal the spring force times the displacement. In that case, when we don't have friction, we introduce something that is called the mechanical energy of the system, which is given by this formula: 1/2 the mass times the velocity square plus 1/2 the spring constant, the displacement square. And this quantity is important because we have shown in the previous video that the Newton's equation of motion implies that this quantity here is conserved along the motion. That means the time derivative of that quantity is 0. And conserved means, because this quantity, the derivative is 0, this means that this particular quantity remains constant along the motion and equal the initial amount. So what that means, first, if we do a picture, what that means is, well, this quantity, if we graph as function of time, is constant. And what it means is, if the spring is oscillating faster with more velocity, that means the displacement has to be close to 0 or smaller, because this addition remains constant. When the displacement is the largest, the velocity has to be the smallest. So, again, because this quantity has to be constant along the motion. So the last thing we said on the previous video is what happens in the case that we have friction. So the damping constant or the friction constant now is positive. Then we don't have conservation of this quantity, the mechanical energy, anymore. And what happens is the derivative is actually negative, which means that the function energy is a decreasing function in time, and it's going to approach 0 when these two quantities are small. Because of the square, it cannot be negative. So if it's decreasing and cannot be negative, it has to approach 0. So this is a brief review of what we discussed in the previous video. In this video, we are going to talk about general results and general properties of solutions of this type of equations. And we are going to start with general results, and the main result is the existence and uniqueness theorem that says the following. Suppose we have the differential equation, a second order linear differential equation like we introduced before. And now we consider an initial value problem for that equation, which is finding solutions of that equation, but not all solutions. Instead, we are going to find solution that satisfies two extra, what we call initial conditions, and that is solutions that at a particular time takes a particular value, and solutions that the derivative, so the velocity in this case, the derivative of the solution at that same time takes some particular value. So this is an initial value problem for second order linear differential equations. So we are going to study that problem, and what people have found is the following. If the functions a1, a0 and b, this function here, the non-homogeneous term and the coefficients, are continuous functions on some interval t1, t2. So suppose these functions are continuous on some interval, then that's all we need. Then there exists a unique solution y of t of this whole problem, of the initial value problem in 1, and the solution is defined on the same interval where the coefficients are well defined, on the same interval. And the solution is defined for any choice you like of the initial conditions and for any choice of the initial time, as long as this initial time belongs to that interval. So this is the existence and uniqueness theorem. Some remarks about that is that the proof of the theorem is based on taking the limit on approximate solutions. So we have seen the Euler method for first order differential equations. Well, the Euler method can be also constructed for second order linear differential equations, and that method creates a sequence of approximate solutions, and if done properly, those solutions can be used to prove this statement here. And this is not the only approximation method, but is the one we have seen, and it can be used to prove the theorem. Notice that the equation now is second order, so there are two derivatives in the equation. So to solve this equation, somehow we need to do two integrations. Each time we do an integration, appears an integration constant, C1 and C2. So if we look only for all the solutions of this equation without the initial conditions, the expression for the solution should contain two arbitrary integration constants. Well, that is the reason why this initial value problem has a unique solution, because all the solutions of the equation must have two arbitrary constants. That's why we put two initial conditions, and with the two initial conditions we are able to fix the two arbitrary constants, and then we obtain a unique solution. The uniqueness part is because of these two conditions that select from all the infinity many solutions of the equation, they select only one. And we have two conditions, two initial conditions, because all the solutions here contains two integration constants. The last thing we mentioned about this equation, this equation up there, is notice that we say that the solution exists and is unique, but there is no formula for the solution. So maybe we should highlight this in red just to emphasize that we don't have a solution formula, and this is kind of unusual because for first order differential equations, so equations where we didn't have this term here, and let's suppose the coefficient is 1, or we divide by this coefficient. For these equations here, we have formula for the solutions. And as soon as we put the second derivative, we are not able to find a formula for the solutions anymore. So let's put that in writing. We already have a formula, a solution formula. So we have a solution formula for first order linear differential equations. Recall how we wrote these equations in this way. And we say that we can solve this equation with what we call the integrating factor method. And what was that? We move this term to the other side. We multiply by the integrating factor, let's call it mu. Then we find the formula for the integrating factor. In this case, we find that the integrating factor has to be exponential negative a, where a is the integral of small a. This is the a. And then you can finish the calculation, and you are going to end up that we get this formula for the solution, where, as we said before, a is the integral of the big A, or capital A, is the antiderivative of the coefficient in the equation small a. So we have a formula for solutions of first order equations. As soon as we put a second derivative here, we are unable to get the formula. So that is the main remarks we wanted to do about this theorem. We have now one example, and the example is about the part of the theorem that says when the solutions are defined, where the solutions are defined, and they are defined in the same interval that the coefficients are defined, as long as the initial time is in that interval. To see a little bit what we mean by that, we have an example. And this is the example. Find the maximum domain where the solution of the initial value problem, this initial value problem, is certain to exist. Certain to exist because of the previous theorem. Okay, solution. How do we find the domain? Well, the first thing we need to do is notice that this equation, this differential equation, is not written in exactly the same way as in the theorem. Can you spot the difference? The difference is here the term that multiplies the y double prime has factor 1. And when we have 1 here, that defines all the other coefficients. In our equation, it's not 1, it's a function. So the first thing we need to do is divide the whole equation by this function if we want to use the previous theorem. The previous theorem assumes that this coefficient is 1. So we need to make this coefficient 1 by dividing by that coefficient the whole equation. And we get y double prime multiplied by 1 minus, and now it's 3t, but we have a factor here in the denominator that is t minus 1, and then multiply by y prime. Then we have plus 4 t minus 1 in the numerator, and here this is there. Let's write it again. 4, a nicer 4, t minus 1, now divided by, we have t minus 3, and now we have a t minus 1 coming from the division we did of the whole equation, and this here is equal to t minus 1 divided by t minus 1. So here obviously we can simplify, but we can also simplify here, but there's no simplification over there because we can't. So we have y double prime minus 3t all over t minus 1 multiplied by y prime plus 4, and here is 4 divided by t minus 3 multiplied by y, and here we have t. Okay, that's the equation, and now is where we can say, okay, this here has to be the coefficient a1 as in the theorem, and this here, including the signs in both cases, has to be the coefficient a0, and of course this here is the coefficient, let's put it down here, this is the coefficient b of t. So now we need to find what is the interval where these coefficients are continuous. And well, that is easy, except at 1 and 3, everywhere else is defined. So the equation has continuous coefficients. Now these are the coefficients. The coefficient when the second derivative is multiplied by 1 has continuous coefficients on the interval, the whole real numbers minus the 0.1 and minus the 0.1 and the 0.3, minus these 2 points. So in a picture, so if we do some picture here, the real line, so let's call it t, and let's put here 0. It's not important. The one that is important is 1, 2 is not important, 3 it is, and we continue. So the equation is well defined everywhere else except at 1. So here, and well, we need to take 3. So in between, so in those intervals, in this interval here, and in this, let's try to make a space here so we emphasize that 1 and 3 are not in the interval. So the equation has continuous coefficients on intervals. So negative infinity up to 1, and then we need to make the union of 1 and 3, and then union 3 infinity. So one could say, oh, the solution is defined on the whole thing, but actually we are not certain about that, because these intervals must satisfy another condition. If we go back to the theorem, that the initial time that we have chosen to solve the differential equation has to be in that interval. So this is another condition. And what is our initial time here? Our initial time here is 2. So now, what we can say up to now is that the solution that of the equation, the solutions of the equation are defined either on the interval -infinity 1, or the interval 1, 3, or the 3, infinity. Maybe the solution is defined in the union of this interval. We don't know. For certain, we know that the solution is going to be defined either here, where the coefficients are continuous, or here, or there, wherever the coefficients are continuous. But we don't know if it's going to cross, because there is a discontinuity somewhere there. So to know which of these coefficients in this interval the solution is for sure going to exist, well, then we need to go at the initial condition, as we mentioned before. The initial condition is at t0 equal 2, and that means that this is in the interval 1, 3. So now, the general solution, the theorem above, the existing uniqueness theorem above, says that the solution of the initial value problem exists for sure on the interval d equal 1, 3. That is for sure. Maybe we can extend the solution, but that depends on particular examples. In general, that's all we can say. So this is how we use the theorem to find the domain of the solutions. Two conditions. First, find what the coefficients are, and then find where these coefficients are continuous. These are continuous everywhere except where the denominator vanishes, and then the solution can be defined in either of these three intervals, but we select the correct interval using the initial time in the initial conditions. Now we move on to discuss the properties of homogeneous second-order linear differential equations. Recall, homogeneous means that the b coefficients in the equation is 0. To discuss these properties is useful to introduce a notation that we call operator notation, and is the following. We write the differential equation like this. Notice that right now b could be different from 0. The notation works for homogeneous and non-homogeneous equations. So a differential equation like this is going to be written in this way, which means that all this left-hand side we have given the name L of y. So here L of y is just the left-hand side of the equation. It turns out that we are using this notation L parenthesis y, very similar to the notation of a function f of x, for example, equal x squared, because this is the notation for functions. And actually we are using that notation because this L, now once we introduce this shortcut, it is also a function. L is a very particular type of functions, L, that acts not on a number but on a function, and the result is another function, this function defined here. So L itself is a function. So L is a function, but acts on functions, and the result is another function. Too many functions on the same sentence. So people call this type of things operator or transformations. An operator is nothing more than a function acting on functions. Here we have an example. Find the action of the operator on t cube and the action of the operator on cosine of 2t when the operator, well, I should have written here a little bit better, so let's fix it. When the operator acting on a function is something like that. This L is compute the second derivative, and to that add 4 times the original function. So let's do this exercise solution just to have a feeling of what an operator is and how they look like. So let's start with computing what is L acting on t cube. Well, notice now the operator acts on functions, not just on a single number, on the whole function. And what the operator does is grabs the whole function t cube and computes 2 derivatives to that, and then multiplies by 4 that function. Alright, so then we are going to have a new function. The new function is going to be 3, and the first derivative here is 3t squared, and then we still have to compute one more derivative plus 4t cubed. Here there's not much to do, and when we compute the last derivative we get 6t plus 4t cubed. Well, that's that. So what this function is doing is to the function t cubed is associated the function 4t cubed plus 6t. So that's what this operator is doing. And then if we compute the operator acting now on cosine of 2t, well, it's going to be another function. What function is going to be? Let's compute. We need to grab the cosine, in this case of 2t, and compute 2 derivatives, and then we need to multiply 4 by the cosine of 2t. This is the example we are working with. Let's compute the first derivative. The first derivative is going to be of the cosine is negative sine multiplied by 2, so negative 2 sine of 2t. This is the first derivative. We still need to compute one more derivative plus 4 cosine. Here there's nothing else we should do. Cosine of 2t. And now one more derivative. This derivative of the sine is back the cosine multiplied by 2, so we have negative 4 cosine of 2t, and here we have plus 4 cosine of 2t. So here we can cancel these two terms, and actually this is 0. So in this case the operator assigns the cosine of 2t gives the function 0. So this is more or less how an operator looks like and why we call it a function. It's a function that acts on functions, and the result is another function. Now we show one important properties of these operators, and this is the linearity property. And as we just said, this is a property of the operator. And suppose we have an operator like the one we introduced before. So the operator is L of y, and it's given by computing the second derivative of this function and then multiplying the function by a coefficient and computing, hard to see, but it's the first derivative, and multiplying the function by a0. So this is a second order linear operator. Okay, that operator satisfies the following property. If we do a linear combination with constants, c1 and c2 are constant, arbitrary constants. We multiply c1 by one of the functions and c2 by another function. y1 and y2 are functions, smooth functions. Smooth means you have second derivative continuous. then the operator acting on this linear combination is the linear combination of the operator acting on the individual functions. That property is called the linearity property. And this property has two particular cases. When the two coefficients here are 1, then we have the addition, the operator acting on the addition is the same as the addition of the two operators. And when one of the constant is 0, then we have this other particular case. So you see one coefficient is 0, so it's not there, so it's not there. So if you have a constant multiplied by a function, recall y1 is a function, the constant goes outside of the operator. These are particular cases of this statement here. And the proof is not difficult. The proof is using the fact that these two properties are satisfied by the derivatives, and that's it, and that this is linear. So let's see the proof. The proof is a simple calculation proof, so it's worth doing it here. So we start computing what is L, the operator, acting on that linear combination. To make it simpler, you can do this calculation choosing, for example, C to be 2 and C2 to be 3. So you easily identify by the numbers what the constants are. Once you do the proof for 2 and 3, you're going to see that it's exactly the same, the proof for general constant C1, Y1 plus C2, Y2. Again, replace C1 and C2 by 2 and 3 and do this calculation. And the calculation is, what is that? Well, the operator we are working with is this operator up here, which says whatever you put in the argument, you need to compute two derivatives. So now this is the argument. So we compute two derivatives of that. C1, Y1. Recall that the function of time here is Y1. The other is C is a constant. C2, Y2, function of time. That we need to compute two derivatives. Then to this function, we need to compute the first derivative and multiply by the coefficient a, whatever that is. So a1 is function of time, but we are not, well, we write it. And then here we have c1, y1, which is function of time. I'm not going to write function of time anymore because it's taking a lot of time. Only on the first step. And we need to compute the derivative. Okay, and then the last thing we need to do is multiply by a0, which is also a function of time, the original function, which is c1, y1 of t, plus c2, y2 of t. Okay, now we are not going to write anymore all these times here because it's too long. But what do we need to do now? We need to compute the derivatives. The first thing we need to do. And this derivative, because this is a constant, the constant is going to be outside of the derivative. The derivative is going to act here and here, nothing more. And this second derivative is also going to act only here and only here because these are constants. So what is going to happen is this is going to be equal c1 and the second derivative is going to be only here plus c2 and the second derivative is only here. And then we are going to have a1, function of time, and then c1 and the derivative is going to be only here plus c2 and the derivative is going to be only here. And then the other term stays as it is because it doesn't have any derivatives. c1, y1 plus c2, y2. Okay, what we are going to do now is we are going to distribute this factor. And what we get is something like this. The first terms are the same. They don't have an extra factor. Now we are going to have a1 of t, or let me write it like this. c1, a1 of t, y1 prime, and then c2, a1 of t, y2 prime. And then in the last terms we have c1 multiplied by a0 of t, y1, and then c2, a0 of t, y2. Perfect. And now what we do is we pull common factor all the terms that have c1. We pull c1 common factor on all these terms. This is one term. Here is another term. We're going to pull c1 common factor, and here is the other term. And in the other terms, we pull common factor c2. Here we have c2. Here we have c2. And here we have c2. So if we do that, we are going to have that c1 multiplies y1 double prime plus a1 of t y1 prime plus a0 of t y1, and then plus c2 that multiplies y2 double prime plus a1 of t y2 prime plus a0 of t y2, isn't it? Well, but this is exactly c1, the operator acting on y1, plus c2, the operator acting on y2. And this is exactly what we wanted to show, that the operator that we are working with, this operator in the theorem, satisfies this property, which is called the linearity property. The other property we wanted to talk today is the superposition property, and this is a property that is a property from of the solutions of the linear homogeneous differential equation. And this property on the solution is a property that comes from linearity in the operator. But linearity is the property of the operator. Superposition is a property of the solutions of the equation with that operator. So as before, let's call the operator to be L of y, the same as before. And now the property is the following. Suppose you have two functions, y1 and y2 functions, and they are solutions, each one solution of this equation. By that I mean L of y1 is 0 and L of y2 is also 0. Then, so is this linear combination for every constant c1 and c2. So this function here is given by this expression is also solution of that equation. So if you have two functions, an arbitrary linear combination of these two functions is also solution of the same equation. And the proof is simple. So let's see the proof. The proof is one line, essentially. So we know that whenever we have a linear operator, L acting on a linear combination of two functions, y1 of t plus c2 y2 of t, it doesn't matter what y1 and y2 are, this is always equal c1 on L of y1 of t plus c2 L on y2 of t, because the operator is linear. So what we are using here is linearity. Linearity. Oh, that is an horrible A. Linearity of L. But now we are assuming on top of that that y1 is solution of this equation, this equals 0, and y2 is solution of the same equation, that is equals 0. Therefore, the whole thing is 0. And then the linear combination is also solution of the same equation, and that's it. That's the whole proof. So what we see here is that the linearity of the operator and the superposition property of solutions are two sides of essentially the same property, of the same coin. And notice that the superposition property does not hold for non-homogeneous equation. Here is important that we make this equal 0. For example, if we have solutions of non-homogeneous equations, like suppose y1 is solution of the operator acting on y1 equal 2, and here the operator of acting on y2 is also equal to, but now it's not 0, it's 2. Then the sum, for example, is not going to be equal to, obviously, because what is that? If we compute L acting on the sum, the linearity property says, well, this is L acting on y1 plus L acting on y2. And now we know that the first term is going to be 2, but there is another 2 coming from the second term. So actually this is equal 4, which is not 2. So that's it. In order to have superposition, we need to talk about solutions of homogeneous equations. The non-homogeneous equations don't have the superposition property. Okay, so one more example about the superposition property. Suppose we have again the same general second order linear differential operator, and now let's suppose we have y1, which is a solution of the homogeneous equation L of y1 equals 0, suppose. And suppose now that we have a y2 that is solution of a non-homogeneous equation. So let's put here homogeneous, and here this is non-homogeneous. Let's move these things a little bit out there. Non-homogeneous. That's the main difference between the two functions y1 and y2. Okay, so now let's solve some true or false statements. For example, with that, what happens with the addition of y and y2? I'm claiming here that y1 plus y2 solves equation 1. Is that true? So what I'm saying here, is it true that L acting on y1 plus y2, this is a question, is equal equation 1, so is equal 0? That is what I'm saying in formulas. Well, the only thing, all these theorems are proved with the superposition, and also, well, linearity is again two sides of the same coin. Linearity. So L, what is L on y1 plus y2? Well, we say that this is L on y1 plus L on y2. And now what do we know about L of y1? Well, y1 is the function of this solution of equals 0. Okay, so this is 0. And y2 is the function that is equal the cosine. Oh, okay. So this here is actually is a cosine. It's a cosine of 2t. Okay, so what we are saying here is that this is equal 0 plus cosine of 2t. So the original function is solution of this equation. Well, that is equation 2, isn't it? So what we are saying here is that, let's summarize it here. This implies that L acting on this function y1 plus y2 is actually cosine of 2t. This is equation 2. So, is solution of equation 1? No, it's not. So, false. So now comes the other question. Is this solution of equation 2? So let's put it in formulas. It's asking, is L of y1 plus y2 equal cosine of 2t? Well, we just have seen that yes. So because of that, This is true. So true. No need to do any calculations. Now next question. What about 2 times? That is kind of not very well written. So what about 2 multiplied by y1 of t? Does this solve equation 1? So what we are asking here is L acting on 2y1. Is that equal 0? So well, here we don't, well, this is what the question is, and we say yes. So okay, linearity again. What is L acting on 2y1? We know that this is 2 L of y1, but we know that this is 0. So recall, y1 is solution of the homogeneous equation, so this is 0. So what we have seen is that L of 2y1 is actually 0. So yes, this is correct, and therefore this is true. And I think it's the last question. What happens if we multiply the other function by 2? Does this product solve 2? Equation 2. What is asking is 2y2 now. Is that equal cosine of 2t? Well, we use linearity again. Linearity says that 2 times y2 is the 2 goes outside, and we have L of y2. But notice that L of y2, we say this is equal the cosine of 2t. Okay, so this is actually 2 times cosine of 2t. So we see what we have found, that L acting on that function is not cosine, it's 2 times cosine. It's not cosine. So actually this is not true, so false. You see? So this is more or less how we use the linearity property to figure out several things about solutions of the differential equation. We want to end this video talking a little bit about what is called the general solution theorem. So again, we have our linear operator as usual, and the theorem says the following. If you have y1 and y2, two functions which are not proportional to each other, and these functions are solutions of the homogeneous equation, so notice homogeneous equation, then every other solution of the same equation has to be a linear combination of these two. So that is the general solution theorem. The proof is in any textbook, and what we are saying here is it's important to notice the one important word in this theorem, which is every here, because we already know from the superposition property that if we have two solutions of the homogeneous equation, then any linear combination is also a solution. We know that from the superposition property, so we know that this is solution of the equation. What the theorem says is that there are no other solutions, because it says every solution. So all the solutions of the equation have to be of this form. There are no other solutions. Because of that, two solutions y1 and y2 which are not proportional to each other are kind of important. The non-proportionality and the fact that they are solutions give us all the solutions. So we call any two functions with those properties. So any two functions that they are solutions of the equation and they are not proportional to each other, we call them fundamental solutions. So let's see how this fundamental solution looks like. For example, let's consider this differential equation. You see here we have our operator is going to be defined by the left hand side. We have here, we are going to denote the left hand side by that operator. And what we are saying in this example is we need to show that this exponential and these exponentials are fundamental solutions of this equation. So, introducing the operator notation, what we need to show first to be fundamental solutions is that they are not proportional to each other, and then we need to show that each of these exponentials is solution of the homogeneous equation. Well, but the first part, but property 1 is, well, is trivial. Why is trivial? Well, because it's pretty obvious that we can do the graph, for example, or evaluate exponential negative 3t is not proportional to exponential, what is the other exponential? 2t. Well, it's very easy to see that. Suppose we do the little graph, something like this. Let's put y here, and let's put t there. And, well, recall exponential negative 3t is something. Let's pass through one. Oops, let's pass through one, maybe over there. This is how exponential negative 3t looks like, and the exponential of 2t is something like this. This is exponential 2t. So obviously they are not proportional. So that's why it's trivial. Now the important part is to realize that they are solutions. So what is L acting on y1? Well, we need to grab this is L acting on the exponential of negative 3t. Okay, what is that equal to? Well, that means that, recall, this is our definition of L. What we need to do is we need to grab this exponential, negative 3t, and compute two derivatives. And then we need to grab this exponential, negative 3t, and compute one derivative, and then we need to subtract 6 exponential negative 3t. If you remember from the previous part of the video, well, we have done this calculation. We know what is going to happen, but let's compute it. The two derivatives here is negative 3 squared exponential negative 3t. Here is negative 3 exponential negative 3t, and then minus 6 exponential negative 3t. Okay, so we pull common factor the exponential negative 3t, and we have 9 minus 3 minus 6, so 0. So yes, this is a solution of the equation, and then you can do the same calculation and find out that if you put exponential 2t, it's also true. Well, actually, let's do it. Instead of leave it as an exercise, let's do it. We are kind of doing a long video, but it's gonna be worth it. So what is L acting on y2 now? Well, the same thing that we did before, so exponential 2t. L acting on that, which is gonna be exponential 2t double prime, then plus exponential 2t prime minus 6 exponential 2t. Alright, what is that? This is a 4 exponential 2t, then we have plus 2 exponential 2t minus 6 exponential 2t, and you see what is going to happen. We pull the exponential common factor, and then we have 4 plus 2 minus 6, which is also 0. And these are by the way, the only two exponentials that they are solution of the homogeneous equation. So these exponentials are fundamental solutions of the differential equation. So these two exponentials then are really important because we have found all the solutions of this equation. We have found two exponentials. Try with any other exponential here, put 4 for example, 4t, and you're going to see that it's not 0. These are the only two exponentials that satisfies the equation, and because they are not proportional to each other, then we have found all the solutions of the differential equation. This is what we say here. Find all the solutions of the differential equation. Well, we did, because in the previous example, we showed that these two functions are actually fundamental solutions of the homogeneous equation? Well, that's great, because now the general solution theorem is telling us that this linear combination give us all the solutions of the differential equation. Done. Once you find fundamental solutions, you are done. And so a little remark then is that there are no other solutions. This is what the theorem is telling us. There are no other solutions to the differential equation. You can try any exponential you like, any trigonometric function, any other function. There are not going to be solutions of this equation. Only linear combinations of the two fundamental solutions. This is a good place to stop. See you guys in the next video.